All right, let's continue. Any questions, any comments? Now I want to prove what I said, this symmetry in the first hour. And basically I want to, this is a little bit from the next chapter, but I think it's just a little bit of flavor if you want, not the whole thing. So I want to talk about translation symmetry and what I called Bloch theorem. So what is a symmetry? Like symmetry is like a kind of transformation in your system that doesn't change anything, right? So if you do some kind of transformation and nobody can tell that transformation, that's a symmetry. Like Feynman says, like change without change. You are changing something, but nothing changes. So symmetry is a transformation that leaves, let me call it physics invariant. And I'll tell you what leaving physics invariant means in just a little bit. So we can, for example, think about translation symmetry, and I'm going to be talking about exclusively about this, right? There is like some, I don't know, like there is some coordinate system, and you have some function, I don't know, something like that, right? So this is f of x, and maybe this f of x, this peak, you can think about it like a Gaussian. Peak is at x is equal to 0. And what you want to do is, for example, you want to do translation transformation. You want to translate this. How do you translate this? You just copy it and shift it just a little bit. Now, where is the center of Gaussian, for example? This is x is equal to a. But for this to happen, what should I do? I need to put f x minus a, right? Wherever I see x in my function, I should go and put x minus a. Then I shifted my function by a. So that's the translation. So this is translation. And in quantum mechanics, we do everything with operators. Translation is also done with operator. And translation operator, I'm going to use T. So this is, let me first start with heads, but you know I'll forget it in just a little bit. TA acting on f of x from this picture should be, let me call it first, transformed f. Let me call it f prime, following the book. So that is not derivative, that means f is transformed. And this is equal from here, f of x minus a. Now, what we can do is we can do the Taylor expansion for this, right? So this f of x minus a is equal to f of x minus d over dx f of x times a plus 1 over 2 d squared f of x dx squared a squared dot dot dot. Right? It goes like this. And what I can do is I can think about this derivative like an operator acting on function, right? I just rearrange this. So this is 1 minus a times d over dx plus 1 over 2 factorial a squared d squared over dx squared plus dot 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 acting on f of x, right? And we know the operators are defined by their Taylor expansion. Then I can exponentiate this and write this as e to the minus a d over dx acting on f of x. Good, simple stuff. From here I found my translation operator, right? This f of x minus a is something multiplying f of x. Then this thing multiplying f of x, I just found it. Then my t is equal to e to the minus a d over dx. But I don't want to write this in terms of d over dx. I want to write it in terms of operators we use all the time. And for that, what I'll do is like, so I'll write this as, so let's put minus I here, and I here, right? Minus I times I is 1, and I want to put h bar here and divide it by h bar, and now I have minus I h bar d dx. What is that? What's that? Momentum. Then this is going to be equal to e to the minus I over h bar a times p. Good. So this gives us translation operator in terms of another operator we know. And this identity people sometimes say, so here momentum is generator, it generates, it's like a generator of translation. And typically almost all translation operators have this form. In the rotation we can have this form, in time translation we have this form, but those I'm not going to talk about. Today I just want to understand translation operator, and I want to connect it to periodic potential. Good. And here let's also write a label. So this is translation by A. You can see the inverse of translation, that t to the minus 1 of A is translation in the opposite side. Right? This is t of minus A. And from here I see that this is t dagger of A. Right? From just this identity, because p dagger is p, I is going to go to minus I, so then A will go to minus A to get the inverse of this operator. And from here we see that t dagger A, let me sometimes write as a subscript, sometimes like a function, depending on how nice it looks. So this is t dagger t is equal to t A t dagger, and this is equal to 1. And operators satisfying this condition are called unitary. So this is unitary. It's not Hermitian, it's unitary. And as an exercise, you can think about this, like unitary operators are written in terms of exponentiation of Hermitian operators. Okay, this is like an exercise in your book. So this is how we translate functions, and this is how we translate states. We can also think about translations or transformations of operators. And let's think about this t acting on a psi function, and it is going to give us some transform psi prime. And I want to look at an observable in this psi prime q psi prime is equal to, right? I can just use this condition. This is psi, and this is broad side, so this is going to be t dagger A. If you want, there is like a here. There's like q, and there's ta psi. Now I have like two ways of looking at the same problem. I can either look at the transformations of states, or I can look at the transformations of operators, right? So this one is called active, right? This is like an active transformation. You are transforming the coordinate system, whereas this one is called passive transformation because you are transforming the function itself. So the other way, like active is like you shift the function, passive is you shift the coordinate system. So let's do an example. So example, let's think about position operator after translation transformation, and let's look at its effect on a function of f(x). And what is that? This is t a x. Okay, this is t dagger a t, and this is t a, and this is acting on f of x. And we know what ta does to f of x, right? Ta acting on f of x is going to put x is equal to x minus a in the function. So this is equal to ta x. So this is dagger. This is f of x minus a. Now this x is hitting on something x dependent, right? And it's just going to give whatever x dependence is. This is going to be ta dagger x f of x, right? And now I am applying the t dagger to this entire thing. Oh, sorry, there is like x minus a. Now I am applying this t dagger to the entire thing, and t dagger is what? Wherever you see x, replace it with x plus a, because it's the inverse of ta. So this is going to be x plus a, f of x plus a. I replace x with x plus a, and there's one more minus a, and this is equal to x plus a, f of x. And this tells me, right, from here I can compare. So this is going to be x hat plus a acting on f of x. Good. Therefore, what I found is the transformed operator is the operator plus a, right? Function transform like x minus a, operator transform like x plus a. That's like active versus passive difference. Any questions? So we can think about another operator, which is p. Similarly, let's think about this p. P acting on, let's transform p acting on f of x is going to be ta dagger minus I h bar d dx. Okay, this is dagger, this is ta, this is acting on f of x. And I do exactly what I did. So this is ta dagger minus I h bar d dx. So this is f of x minus a, right? This is what the operator does. Now this operator is going to act on this, and wherever you see x, replace it with x plus a. So this is minus I h bar d over d x plus a, f of x plus a minus a. But derivative, right, d over d x plus a, if you change the variable by a constant, derivative does not change, d over dx. So this is minus I h bar d over dx f of x. And from here we see p prime is actually equal to p, right? This is p times f of x. Then p is transformed without any change. Good. Now, when do we say there is like a translation symmetry? Let's talk about that. So we say there is translation symmetry in our system if the Hamiltonian, right? The Hamiltonian is a special operator, and now we know how operators transform. If the Hamiltonian does not transform, like this h is equal to some TA dagger H. Okay, this is if you want TA, right? This is what we call X prime or P prime. Now in this case H prime. So this is H prime. If H prime is equal to H, we say, okay, these are all operators. Then we say there is translation symmetry. Right? Now let's use this H being equal to H prime. Okay, let me do this like that. So if H is equal to H prime, I have TA dagger H. TA is equal to H, and I can multiply both sides with TA, and TA dagger, because it's unitary, is going to be 1. I have H TA is equal to TA H, or I can combine them on the same side. This is minus 0. Therefore, if there is translation symmetry in my system, Hamiltonian commutes with translation operator. So if this is given to us, this means we have translation symmetry. Simple stuff. And for example, for this thing, we can consider like our usual Hamiltonian, right? Most generic Hamiltonian is like H is equal to P squared over 2m plus V of X. And if we transform with like some translation operator, right? P doesn't transform, but X, wherever you see X, you put X plus A, right? H prime is equal to P squared. Okay, H prime is defined by this TA dagger H TA, and it's equal to P doesn't transform. This is P squared over 2m plus V of X plus A. And if there is translation symmetry, that means H prime is equal to H, right? H prime is equal to H. Then P squares are the same. The only requirement is V of X should be equal to V of X plus A. Or another way to say is we need to have periodic potentials. So that's exactly what we did in the first hour. And there are two cases that are important technically. The case one, which we consider in the first hour, is discrete translations. And in that case, H is equal to TA dagger H TA for discrete A, something like A plus or minus, okay, plus or minus A, plus or minus 2A, plus or minus 3A, and so on, exactly like what we had in the first hour. And case 2 is continuous translations. And this one is, again, H is equal to T dagger H T for all A. For all A. And now I want to consider this discrete translation symmetry and show you Bloch theorem. And it is like you are going to see it's like a very simple application of our rule in quantum mechanics, right? If two operators commute, they have common eigenstates. That's what Bloch theorem is, with the operator being translation operator. So let's consider so given, to prove Bloch theorem, we only need given Hamiltonian commutes with translation operator, and A is discrete for discrete A. And we know, right, this is our one of most important theorems we used repeatedly in this semester. If this is the case, H and TA can be diagonalized simultaneously, or they have common eigenstates, or they have common eigenbases. So what are their eigenvalue equations? First, we have the time-independent Schrödinger equation, H psi of x is equal to E psi of x. Right? This is an eigenvalue equation for Hamiltonian, and the same psi should have an eigenvalue for T2, like TA times psi of x. Let's call it lambda times psi of x. Good. And since Hamiltonian is Hermitian, it has real eigenvalues. We proved that. Let's also consider the eigenvalues of unitary operator, right? Now T is not Hermitian but unitary, right? TA dagger TA is 1. Now we can consider this psi, which is for any state is going to be just insert TA dagger TA here. So this is psi TA dagger TA psi. So this piece is going to be lambda times psi. This piece is going to be lambda star. And from here we see this is equal to lambda squared psi psi. And then that means lambda squared is equal to 1, or lambda should be something like e to the I alpha phase. Good. But like in the Bloch theorem, we don't call it alpha. Here, I'm going to put this in exactly the form we used, but for the moment I want to call this phase minus I q times A. And hopefully you are seeing that we are trying to connect there. And in this q, h bar q, so there's like terminology, is called quasi-momentum, or sometimes crystal momentum. Okay, now let's think about this eigenvalue equation for translation operator. So this is TA acting on psi of x is lambda times psi of x. But we know this is also equal to psi of x minus a. Right? That's what the translation operator does. Therefore, we have psi of x minus a is equal to e to the minus I q a psi of x. And we proved Bloch theorem, right? Actually, we didn't do anything, but that's the Bloch theorem. So this is also what I used in the first hour. So this is Bloch theorem. Good. Sometimes we also use Bloch theorem in a different version. Let me also show you how to get that. Let's define a function u of x. So this is the definition of u. I want to define and see the properties of this function. And the definition is minus I qx psi of x. And now let's put in here, wherever we see x, let's shift it x minus a. So what I have is u of x minus a is equal to e to the minus I qx e to the I qa. I split this, and psi of x minus a. Good. Now I use this, right? Wherever I see psi x minus a, I just write e to the minus I qa psi of x, and this one are going to cancel, and I have e to the minus I qx psi of x. and I look at this e to the minus iqx times psi of x, I just define this here. So this is u of x. That means this u I defined is periodic. U of x is equal to u of x minus a. Or another way to write this, I can write psi of x as e to the, right, I now multiply both sides with e to the iqx and u of x, and the condition on u is u of x is equal to u of x plus or minus a. Let me write plus a. And this is also sometimes called Bloch condition or Bloch theorem. So this is also Bloch theorem. You can see because we used the first one to derive this one, they are exactly the same thing. It's just like rewrites of the same condition. And the key here is like very important, like, and most people jump to this generally, psi of x plus a is not equal to psi of x. I mean, Hamiltonian is periodic, but it doesn't mean wave function is periodic. Rather than that, we have psi of x plus a is e to the I qa psi of x. There is like a phase degree of freedom with the translations. And that's the essence of Bloch theorem. And this also tells us something like, in my opinion, very surprising, right? So in like a solid, you have like infinitely many like ions, right? You just put like, in a crystal you have Avogadro's number of ions, millions and millions of ions, and you put electron here, and somehow electron still has a wave, right? It's like a wave, like it's exactly like plane wave, but there is like some modulation. So electron doesn't even see the crystal, even though there are like so many centers to, you know, collide and backscatter. Electron doesn't do that. Electron finds a way to go freely as if there is nothing in the crystal, right? And that's quantum mechanics. And okay, electrons are like free electrons in crystal. And we actually sometimes explain this with so-called Bloch condition, because electrons are wave, they scatter, but because the scattering is constructive, they just can propagate in the crystal. And again, if you want to see more details on this, I recommend you go and take Physics 409 next year. Good. Any questions? So this was case 1, the discrete symmetry. Now let's consider the continuous symmetry. I will try to finish after that. So case 2, continuous translation symmetry. So if, okay, in this case, if H TA is 0 for all, right, small or large for all possible A's, we say we have continuous translations. So this is the case. Then if that's the case for all A, we can take A to be infinitesimal. Like let's take A is equal to some delta small. Okay. So that's also a translation. Then T of delta is like an infinitesimal. What is it? It is e to the minus I over h bar delta times p. We derived this a moment ago. But because delta is so small, we don't need the exponent. We just can expand it and take the first one. So this is very closely equal to minus I over h bar delta times p. Good. Now I want to put this in here. So there is h 1 minus I over h bar delta p P is equal to H1. This is like a constant, right? Constant just commutes, so we can just get rid of that. So this is like an overall constant. We can also get rid of that. This means this is like minus I H bar, minus I over H bar, delta H. Okay, H is an operator, P is an operator. And what is it? This is 0. But if this is 0, we see H and P is 0. And what we found is if there is continuous translation symmetry, Hamiltonian and generator of translation symmetry is momentum, then Hamiltonian commutes with momentum. Okay, so that's what we see. And from our like generalized Ehrenfest theorem, what do we know about expectation value of dp dt? So let's look at it. The dt expectation value of p. We know from generalized Ehrenfest theorem this is hp. You can go check your notes. But we just found h and p commutes if there is continuous translation symmetry. That means this is 0. Therefore, expectation value of momentum is constant and does not change. And if something is constant and does not change, what do we call it? Like, for example, energy is constant and doesn't change. What do we say? It's conserved. That means if H and P commute, or like if there is translation symmetry, H and P commute, and that means momentum P, or like let me write momentum, then momentum is conserved. So there is also another definition in your book, you can also check it out. So this, we defined conservation in terms of expectation value. But you can also look at in terms of its eigenvalues, right? If you make a measurement, it's going to give like a certain eigenvalue with a certain probability. That also doesn't change with time if there is continuous translation symmetry. And you can read your book if you are interested. But now I want to take you to upshot. So what is the upshot? There is like a symmetry. So in our case, this is continuous translation symmetry. And from symmetry, what did we find? We find that there is like a commutation relation. So H and P commutes, right? Symmetry means something commutes with Hamiltonian in quantum mechanics, right? So this is commutation. And if something commutes with Hamiltonian, we know they have common eigenbases, right? That's like our commutation theorem. So then generator of symmetry has common eigenbases with H. And what does that mean? That means this generator is conserved. Observable is, in this case, momentum is conserved. Right? If something is conserved, we connect it to commutation and we connect it to symmetry. And you can go in either way, right? I say go this way, but if something is conserved, we can go and say it's like commutes with Hamiltonian, and it's going to always imply a symmetry. Good. So this is, if you want, conservation law. But in our case, we like this can be tricky and like very enjoyable, right? It's one of the nicest areas in quantum mechanics. But in our case, we just consider only the simplest translations. Good. Any questions or any comments? If not, I'll stop here. Thank you.